Good morning, everyone. Thank you for joining us today. We're embarking on a crucial journey into system integration and diagnostics. Now, if you join us for our last deep dive, you'll remember we spent time sort of deconstructing the computer, looking at parallel processing and specialized accelerators. Today, we're flipping the script. It's really all about synthesis, bringing those individual parts back together. This is where, the theory becomes reality, where a box of parts turns into a powerful machine. So if you've ever thought about building your own PC, or maybe just wonder what happens, what complex dance goes on when you hit that power button, well, this deep dive is definitely for you. We'll get into selecting the right components, walk through assembly, demystify that boot sequence, and hopefully arm you with some knowledge for troubleshooting common hardware faults. And to guide us through this intricate landscape, we're once again joined by our insightful expert. Welcome.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
Absolutely. Great to have you. So we'll kick off with component selection, compatibility, getting that right, then the physical assembly steps. After that, peel back the curtain on the boot sequence, what's really going on there. And finally, touch on troubleshooting. When things don't quite go to plan, let's dive right in. Component selection. When you're building a system, it's really tempting to just grab the fastest, most powerful part for every single slot, right? But the sources we looked at really stress this idea of a balanced system. So maybe for someone newer to this, or even someone experienced just tweaking a build, what exactly is a balanced system, and why is it so critical for performance?
That's a really fundamental starting point. A balanced system, it's one where each component is, let's say, well-matched with the others. It's definitely not about just buying the absolute top-tier part in every category. That often leads to bottlenecks. Performance bottlenecks. Think of it like this. Putting a Formula One engine in just a regular family car. The engine's incredibly powerful, sure, but the rest of the car, the chassis, the brakes, the tires, they just can't keep up. They can't utilize that power.
So you've wasted potential.
Exactly. You've spent all this money on the engine, but its full potential is held back. In a PC, it's similar. A super high-end graphics card with, say, a low-end CPU. The GPU is just going to sit there waiting for the CPU to feed it data. You're leaving performance on the table. So harmony, getting everything working together efficiently, that's the key to maximizing your investment.
That F1 analogy really paints a picture. A symphony of parts, not just soloists. Okay, so thinking about balance, where do you start? What's the absolute first compatibility check a builder needs to make, the real foundation?
The absolute bedrock. It has to be the CPU and motherboard handshake. That's non-negotiable. The CPU you pick must physically fit the socket on your motherboard and electrically match, of course. You can't, for instance, put an Intel CPU into an AMD socket or vice versa. They're physically different.
Right. Different pin layouts, different mounting.
Totally different. And even within the same brand, you can't usually put a brand new CPU into a really old socket. Think Intel's LGA 1700 or AMD's AM5. Those are current examples. And here's a nuance. Even if it physically fits, the motherboard's chipset also has to support that specific CPU.
Ah, okay, so it's not just the socket type.
No. Sometimes an older chipset might technically accept a newer CPU physically, but it won't actually recognize it or work properly without a firmware update, a BIOS or UEFI update. And for a new builder, doing that update can be tricky if you don't have an older, compatible CPU handy just to perform the update itself.
That sounds like a potential catch-22, a hidden hurdle.
Well.
Okay, CPU and motherboard sorted. What about RAM, another crucial piece? What compatibility rules apply there?
RAM's next, definitely. The main thing is the generation, DDR4, DDR5, and so on. Luckily, they're physically keyed differently. The little notch on the bottom edge of the RAM stick is in a different place for each generation.
Oh, so you can't physically put DDR5 into a DDR4 slot?
Exactly. It just won't go in without breaking something, which is a good safety feature, actually.
Yeah, prevents expensive mistakes.
It does. But beyond just fitting, you absolutely have to check the motherboard spec sheet. Its QVL, or a qualified vendor list, is even better. That sheet tells you the maximum amount of RAM supported, how many slots you have, and critically, the reliable speeds it's tested to run that memory at.
So just because RAM says it's fast doesn't mean the motherboard can handle it at that speed.
Precisely. You might buy super fast RAM, but if the motherboard isn't rated for that speed, it might default to a slower standard speed, or worse, cause instability if you try to force it.
Okay, good to know. Check the specs. So we've covered electrical compatibility. What about just plain physical space? Fitting everything inside the case. what spatial checks are essential?
The "it just won't fit" moment.
Yeah.
That's a classic builder frustration. Happens more than you'd think. You need to think in 3D. First, case and motherboard form factor. Obvious one, maybe, but crucial. An ATX case fits ATX boards, micro ATX, mini ITX. But you can't put a big ATX board in a tiny mini ITX case.
Makes sense. Size matters.
Definitely. Second, GPU length. Modern graphics cards, especially the high-end ones, are, well, they're huge. Long.
Like bricks, some of them.
Exactly. You must check the maximum GPU length your case supports in its specs. Otherwise, it might literally hit the front fans or the hard drive cages. No room.
Oh, yeah. I can picture that being a problem.
And third, related, is CPU cooler height. Especially if you're using a big air cooler, not liquid cooling. Those tower coolers can be really tall. Again, check the case specs for maximum CPU cooler height. Make sure the side panel will actually close when it's installed.
Seems basic, but easily overlooked in the excitement of picking parts. I've definitely heard stories.
Oh, me too. Measure twice, buy once. Right.
Absolutely.
Yeah.
Okay, final compatibility check. Power, the PSU. How do you make sure it's right, both in terms of power delivery and physical connections? This feels like an area where getting it wrong could be bad.
Power is critical, yeah. The power supply unit, the PSU, needs enough stable power for everything. And it's not just about the total wattage number on the box, though that's a starting point. What's really crucial is the power available on the plus 12V rail.
The plus 12V rail, why that one specifically?
Because that's what powers your most power-hungry components, the CPU and the graphics card. You could have a PSU with a high total wattage, say 800 watts, but if its plus 12V rail is relatively weak, it might struggle to power a high-end GPU under load. It could cause crashes or prevent the GPU from reaching its full speed.
Ah, okay, so look at the detailed specs, not just the big number.
Definitely. And beyond the wattage, you also need the right physical connectors, especially the PCIe power connectors for the graphics card. Older cards might need one 8-pin connector. Newer, powerful ones might need 2 or even 3, or the newer 12 plus 4-pin connector. Your PSU has to have the specific cables your GPU requires.
Right. Those connectors seem to change quite often with new GPU generations.
They do. Always double check.
Okay, that's a fantastic rundown on selection and compatibility. So, let's say we've carefully chosen our balanced, compatible parts. Now comes the assembly. This seems like the most daunting part for many. What's the absolute first, most critical thing to do before you even open an anti-static bag?
Okay, before touching anything sensitive, the #1 priority is electrostatic discharge, ESD prevention.
Static electricity.
Yes. It's invisible, but the static charge you can build up just walking across a carpet can be enough to instantly, permanently damage components like the CPU, RAM, motherboard. It's a silent killer for electronics.
Oh, so how do you prevent it?
The bare minimum. Periodically touch a large, unpainted metal object. The metal frame of the computer case itself is perfect before you pick up any component. That grounds you, discharges any static buildup.
Okay, simple enough.
But the professional best practice, and what I'd strongly recommend, is using an anti-static wrist strap. You wear it on your wrist and clip the other end to a grounded metal point, like the case. That keeps you continuously grounded.
Worth the small investment then, sounds like.
Absolutely. Saves potential heartache and, well, money.
Right. So, grounded and ready. Which components are best installed onto the motherboard before putting the motherboard into the case? Does it make it easier?
Oh, definitely easier. You have much more room to work, better light, better angles. So before the motherboard goes in the case, install these. First, the CPU. Open the socket lever. Carefully align the little triangle or notch on the CPU with the corresponding mark on the socket.
Okay.
Gently place it in. It should drop in with 0 force. Then close the lever. Done. Next, the RAM. Open the clips at the ends of the RAM slots. Align the notch on the bottom of the RAM stick with the bump in the slot. Press down firmly and evenly on both ends until the clips on the sides click into place, locking the stick.
Do you feel solid?
Exactly. Then if you have an M.2 SSD, those little gum stick drives, install that. It usually slots in at an angle. Then you press it down flat and secure it with a tiny screw. And finally, the CPU cooler. This varies a lot depending on the cooler type.
Air cooler versus liquid, yeah.
Right. But typically it involves attaching a mounting bracket to the motherboard first. Then apply a pea-sized dot of thermal paste onto the CPU lid. Then you mount the heatsink or water block onto the CPU and secure it according to its instructions. Doing all this outside the case is much, much easier.
Tackling those fiddly bits with open space sounds much less stressful. Okay, motherboard prepped, components installed. Now it goes into the case. What are the final major steps to get everything connected?
Right, so first, make sure the motherboard standoffs are installed in the case in the correct positions for your motherboard size. Little brass or black pegs.
Ah, to lift the motherboard off the case metal. Prevent shorts.
Yeah.
Exactly. Crucial step. Then you carefully lower the motherboard onto the standoffs and secure it with screws. After the motherboard is in, you install the other major components. The graphics card goes into the topmost long PCIe slot, usually labeled by 16. Any traditional storage drives, 2.5-inch SSDs, or maybe older 3.5-inch hard drives get mounted in the case's drive bays or brackets. Then you mount the power supply unit in its designated spot, usually at the bottom or top rear of the case.
Okay, all the big pieces are physically in place. Now the wiring.
Now the wiring. This is often the most time-consuming part. You connect the main power cables, the big 24-pin ATX connector to the motherboard, the smaller 4 or 8-pin CPU power connector, usually near the CPU socket.
Right.
Then the PCIe power cables and the PSU to the graphics card. Remember those we talked about?
Okay.
Connect SATA data cables from the motherboard ports to your SATA drives, and also SATA power cables from the PSU to those drives. And then the fun part, the front panel connectors.
Oh, those tiny little wires for the power button, reset button, USB ports.
Those are the ones. Power LED, hard drive activity LED, front audio jacks, front USB. They connect to a block of pins on the motherboard.
Yeah.
And this is where your motherboard manual is your absolute best friend, because the layout of those pins varies wildly. Getting them wrong usually just means the button or light won't work, but it's fiddly.
I remember squinting at diagrams for those.
We've all been there. Lastly, before you button everything up, cable management. Take some time to route cables neatly, often behind the motherboard tray, if your case allows.
Not just for looks.
Not just for looks, good cable management significantly improves airflow inside the case. Better airflow means better cooling, which leads to better stability and potentially longer component life, especially under load.
Right, keeps things cool and running smoothly. Okay, wow, that's the assembly. Meticulous work. So the system is built. Connections triple-checked, moment of truth. You press the power button. What actually happens in those first few fractions of a second? That invisible magic.
It is like magic, but it's a very precise sequence. Pressing the power button signals the PSU. The PSU does a quick internal self-check, make sure its own voltages are stable. If everything's okay internally, it sends a signal called power good to the motherboard.
Power good, okay.
Once the motherboard receives that power good signal, it immediately activates the CPU, wakes it up. The CPU's very first instruction tells it to start executing code from a special chip on the motherboard, the BIOS, or more commonly now, the UEFI firmware chip. That firmware is like the system's fundamental pre-operating system brain.
Incredible how fast that happens. Power, check, CPU on, load firmware, okay? And part of that initial firmware process is the POST, right? Power on self-test. What does that do?
Exactly. As soon as the firmware starts running, it initiates the POST, the power on self-test. This is a critical, very quick diagnostic routine. Its job is to check for the presence and basic functionality of the absolute essential hardware needed to even start the boot process. So, it checks. Is the CPU working? Is the RAM detected and minimally functional? Is there a graphics card present? Is a keyboard connected? If any of these fundamental checks fail, the POST halts the boot process right there. It won't continue if a critical component is missing or faulty. It's the first line of defense.
A vital check. So if it does fail, how does the motherboard tell you what's wrong? I remember old computers making annoying beep guns.
Ah, yes, the beep codes. Trying to decipher those was an experience.
Like Morse code for computer problems.
Thankfully, modern motherboards are much better. Most now have a set of small debug LEDs right on the board. They're usually labeled something like CPU, GRAM for RAM, VGA for graphics, and boot for storage device issues. If the post fails, one of those LEDs will typically light up and stay lit, telling you exactly which component group caused the failure. It's hugely helpful for troubleshooting.
That is a massive improvement. Pinpoints the problem area right away. Okay, so let's say POST is successful, all green lights. What's the next step? How does it get from there to loading Windows or Linux?
Okay, POST passes. The firmware then initializes some other connected hardware. After that, it looks at its configuration settings to find the boot order.
Boot order, like which drive to check first?
Exactly. It's a priority list. Check this SSD first, then maybe this other drive, then maybe a USB drive, etc. It searches the storage devices in that specified order, looking for a specific piece of software called a bootloader. The bootloader is a small program whose only job is to load the actual operating system. Once the firmware finds a valid bootloader on a drive, It loads that bootloader into RAM and then essentially hands over control of the computer to it. The bootloader then takes over and starts loading the main OS kernel, Windows, Linux, macOS, and all the necessary drivers into memory. That's when you start seeing the familiar OS loading screen.
Fascinating sequence. Firmware finds bootloader loads OS, or rapid handover. Now, you mentioned the UEFI or BIOS firmware. Beyond just booting, it's also where you configure things. What's one really critical performance setting in there that builders should definitely look at?
Ah, yes. For performance, one of the most important settings to enable in the UEFI is for your RAM. It's called XMP, Extreme Memory Profile, on Intel platforms, or XPO, Extended Profiles for overclocking, on AMD platforms.
XMP or XPO, what do they do?
Your RAM modules actually have these profiles stored on them. They contain the settings, speed, timings, voltage needed to run the RAM at its full advertised speed, which is often much faster than the default standard speed. If you don't enable XMP or XPO in the UEFI, your expensive fast RAM will just run at a slower, safer default speed, called the JDEX speed.
So you're leaving speed on the table if you don't turn it on.
Absolutely. Significant speed, often. It's usually a very simple setting to enable. Just find it in the UEFI menu and turn it on. Of course, the UEFI is also where you set the boot order we just talked about, set the system time and date, maybe tweak fan speeds for noise or cooling, and enable security features like Secure Boot.
Right. Essential tweak for getting what you paid for from your RAM. Okay. We've covered selection, assembly, the boot sequence. But, reality check, sometimes things just don't work right. A new build won't start or an old system gets unstable. How should someone approach hardware troubleshooting? What's the mindset?
Troubleshooting.
Yeah, can't be frustrating.
But the key is a logical, methodical process of elimination. Don't panic. Just work through the possibilities. Let's cover a few common scenarios.
Okay.
Scenario 1. The system won't power on at all. You hit the button, nothing happens. No fans spin, no lights turn on, dead silence. This almost always points to a power delivery issue. First checks. Is the power switch on the back of the PSU itself flipped on?
Easy one to miss.
Very easy. Is the wall outlet working? Plug a lamp into it to check. Is the power cord plugged in securely at both ends? And double check that the case's physical power button wire is correctly plugged in to the right pins on the motherboard's front panel header. That little connection tells the motherboard to start.
Got it. Basic power checks first. What about scenario 2? This one seems common with new builds. System powers on, fans spin, lights on, but no display output. And maybe those debug LEDs are lit.
Ah, yes. The it turns on but does nothing problem. Very common. Powersupply is failing. Here, you need to methodically check the core components and their connections. Start with power connections again, but inside the case this time. Reseat, meaning unplug and firmly plug back in the main 24-pin motherboard power connector. And critically, reseat the 4-pin or 8-pin CPU power connector. This one is so often missed or not fully seated, and it will absolutely cause a no-post-T situation. The system seems on, but the CPU has no power.
That specific CPU power plug.
Also reseat the PCIe power connectors going to the graphics card if it needs them. Make sure they're clicked in. Next, RAM. Take the RAM sticks out, then put them back in firmly, making sure both clips lock. If you have multiple sticks, try booting with just one stick installed, testing each stick in the primary slot. Maybe one module is faulty.
Good idea. Isolate the RAM.
And then the GPU. Make sure the graphics card itself is fully pushed down into its PCIe slot. Reseat it. And here's another super common mistake. Make sure your monitor cable is plugged into the port on the graphics card, not into a video port on the motherboard's main I/O panel, unless you're intentionally using integrated graphics and don't have a separate card.
Ah, plugging the monitor into the wrong place. I can see that happening.
Happens all the time. Check the GPU outputs first.
Okay. What about instability? Like, the system boots into Windows, but then you get crashes, blue screens of death, BSODs, random restarts.
Right, BSODs and random crashes. System boots, but it's flaky. Several likely culprits here. First, unstable overclock, or XMPexpo. If you enabled XMPexpo for your RAM or manually overclocked your CPU, the very first troubleshooting step is to go back into the UEFI and disable it. Set everything back to default speeds. See if the system becomes stable.
So rule out the performance tweaks first.
Exactly. Sometimes the advertised profile just isn't perfectly stable with your specific combination of parts. Second, potentially faulty RAM. Even if it passes post, RAM can have subtle errors that only show up under load, causing crashes. The best way to test this is to run a dedicated memory diagnostic tool like memtest86. Let it run for several hours, ideally overnight. It'll report any errors.
memtest86, okay.
Third, overheating. If crashes happen mostly when gaming or doing heavy tasks, check your CPU and GPU temperatures using monitoring software. HW monitor or similar tools work well. If temps are getting really high, like CPU over 90 degrees C, GPU over 85 degrees C under load, though exact thresholds vary, it points to a cooling problem. Maybe the CPU cooler wasn't mounted properly, maybe thermal paste needs reapplication, or maybe the case just doesn't have enough airflow.
Check temps under load. Makes sense. That's a really practical set of steps for common issues.
So to kind of wrap all this up, taking us from that box of parts we started with all the way to a working diagnosed PC, what's the overall journey? Yeah, summarizing the whole thing, it's really a satisfying journey, I think. It takes that theoretical knowledge of how computers work and makes it completely tangible. It starts not with building, but with careful thought. Selecting components for balancing compatibility to avoid those performance traps. Then comes the assembly, which isn't magic, but a logical sequence. Preparing the motherboard, installing parts, managing cables, always keeping ESD prevention in mind. The magic happens at first boot, that rapid sequence from power on, through the PSU check, the firmware loading, the critical POT diagnostics, checking core hardware, and then the handover to the bootloader, which finally brings your operating system to life. And that UFIDIOS isn't just for booting, it's your control panel for tuning performance, like enabling XMPEXPO and setting up security. And finally, knowing that when things do go wrong, which they sometimes do, you have a methodical process for troubleshooting. You can eliminate possibilities, diagnose the fault, and fix it. It really transforms you from just a user into someone who understands the machine at a much deeper level. It's quite empowering, really, to understand these complex devices that, run so much of our modern world.
What a journey is right. Empowering is a great word for it. From these separate, almost inert pieces of silicon and metal to this incredibly complex, dynamic system, it really underscores how much sophisticated engineering we interact with daily, often without a second thought. It's a reminder that beneath all the software abstractions, the physical hardware, meticulously assembled and configured, is where it all begins. Pretty amazing stuff. Well, that wraps up another deep dive. We hope this journey through system integration and diagnostics was insightful. Please join us for our next series, where we'll venture beyond the desktop. Mobile and embedded architectures should be fascinating.
Thank you, everyone, for listening today. It was a pleasure.
And thank you for joining us. We hope you enjoyed this exploration. Remember to subscribe to our channel, Tech, AI, and Beyond, so you don't miss our next deep dive.